So this is the software RT-LAB. So it's an interface that lets you design and model your simulations, and it's based out of MATLAB Simulink. So it basically takes a MATLAB Simulink model and it moves it to real time so you can simulate it. So let's actually take a look at one of those models. This was a project we actually did with Total Energy and Cinergia. So it's an example of an actual project we've used for this development. So this here is the real-time model. So it's an example of a microgrid model. So as you can imagine with Cinergia, you don't have enough kind of computational resources on the device to model battery system, wind systems, PV systems all at the same time, and then combine them together onto a grid. So that's what we use the Opal for. So up at the section here is where we actually have that grid portion. So we have our simulated AC grid, transformers, circuit breakers. We've got our loads, which include sheddable loads, demand response for loads, and critical loads. So we're simulating all of their demands. We have a wind turbine generation model. And again, these are all being simulated in real time. So every 50 microseconds, all of these steps happen together. Diesel generators, battery storage systems, PV systems. And then down here, which we'll get to in a second, is where all of that grid connects with the Cinergia. So this full simulation is happening, and we actually connect it directly to the Cinergia system. We have controls for each of these components. So our wind turbine has control measurements inside of it, where we can manage, for instance, the tilt or the other information about it. We can set what's the wind speed. We can do our mechanical determinations. We have our PLLs, for instance, so the components match. We're simulating it down to that level of PLLs and devices like that. So we can really model in detail, if I play with my wind turbine model, how can I improve my microgrid's efficiency? Things like that. Our diesel generator, how can we minimize power uses on our diesel generator to still maintain, stability? But we can do all these kinds of measurements here, and we can also do over here all these different kinds of control. So here we just have essentially a couple of trip signals and other, standard commands for our droop control, things like that. We have those abilities to command all of those systems. If you folks have used SPS or MATLAB, like SimScape power systems, similar idea, right? It's what we have here, where we can actually simulate these power connections that have voltage and current and everything traveling along. So it's a 3-phase microgrid with all this integration. Over here, we actually simulate the high-level microgrid controller that's supervisory, manages all these different resources, and then assigns which one are going to activate, how am I going to change their function, things like that. All of this happens in the simulator. So this is like an example of a very complex system we would want to do in our simulator, as opposed to like a GE mode where you can add harmonics, but you can't necessarily reflect this much larger system. And then where we actually connect it in is our interface here. So in this case, we have down here, it looks surprisingly simple, but this is actually what the VITM method means. So we have this connection to our grid, and over here, we have our set of voltage measurements. So we measure these voltages, we convert them to analog signals, and we send them to the Cinergia. The Cinergia then creates those voltages that match our microgrid. It's connected to whatever it might be, right? It might be a battery system, it might be a load, it might be an inverter, whatever the arbitrary device is. We then measure from the Cinergia, what is the current draw from this device? We then inject the current into the system. And so these current sources here act to match what that physical system is doing. So we send out voltages. Think of a resistive load, right? It's a very simple, basic idea. We're sending out 100 volts to a 1 ohm resistor. So we're going to draw 100 amps. I'm using round numbers. That 100 amps measurement is going to come back here. And now in our model, 100 amps will be pulled by the resistor. If we change the voltage on the microgrid and go to 200 volts, it's then going to increase the current to 200 amps. So now our simulated system and our real system are connected via this interface. We have the snubber load here. So like I mentioned before, this is a way to help suppress some oscillations and improve the stability of this section because of essentially the mathematics of current sources, right? You're going to get oscillations like we saw as it tries to respond to step changes. So by snubbing it, it helps suppress those a little bit. So this is, again, the ITM interface method. It's very, very simple, and it works pretty well overall. You can add in here, for instance, if let's say we wanted to add in the most basic of filtering algorithms, we could add like a low pass filter here. So a low pass filter would filter out all the high dynamics and would maintain a range of stability. So we would lose some accuracy because we're filtering out high dynamic signals. We're improving stability of our model because we're allowing it to change more gradually to different kinds of responses, right? There is a set of different like essentially conversions. So here we have to take whatever our amplifier voltage is and we have to scale it. We have to scale that voltage to an analog voltage, right? We might be doing 240 volts, but we need to scale that then to a 10-volt signal to command with Cinergia. So we do that conversions. We have things like slew rate protection. So this Cinergia is not going to suddenly get a massive step jump, which could be problematic. These kinds of protections to help manage that signal interface. We also have, like I mentioned, we can scale it. So there is the options here to include like different scaling options, filtering options, so we can have in those low pass filters. We can basically use different transformation methods optionally if we want them here. And then finally, here, it takes those signals that we've generated and it takes them and sends them to the Cinergia. So whatever those values are, at the other way, it also takes in data, which goes through this interface algorithm itself. And so now going back to like, all of this, everything here, all of these things are simulated. The controllers, for the microgrid, the power systems, the inverters, transformer, grid connection, all of this is simulated in real time. So if we have a fault or another mistake, we can respond to that. This component down here is where the real world connects to our simulation. So we connect our Cinergia to this model. So now our Cinergia acts as if it's part of this and lets us bridge the physical world with the simulated world to see how these large systems might react. So if you're working on, for instance, this case, a microgrid, they want to develop microgrid controllers and protection relays and things like that. They could interface them here, but the nice thing is this simulation does not know and does not care what that device is doing, and that device doesn't have to know about this. From both perspectives, it's as if it's in the real world. This inverter is getting power signals as if it was in a real microgrid and it was reacting to real power. So you can see how it's going to react in those environments. So you could simulate things like what happens if the diesel generator or another device begins to overload, or the battery system goes out, or there's an islanding event because the grid goes down. How is your device going to react to that situation, and what is it going to do? And on a simulated side, how can I improve my other controllers that are simulated? So you don't have to have 5 or 6 inverters set up. You have one inverter set up, and the rest of them are happening in like a digital space. So you can control them very accurately. So that's kind of where all of this comes together, is we run this model in real time. So I think this one runs every 50 microseconds, so 20 kilohertz. So with 20 kilohertz and you have a 50 hertz grid, you get a lot of data points that you can do. So you can capture fairly high dynamics in this case, and then actually run your like stuff. So that's kind of the closing the loop of what you can do with real time. You can obviously command it and change things in real time. So we have here like all of the commands and controls. You have different scopes you can view, so you can do that. You can always use like an oscilloscope as well, so you can connect that. You can see the power signals, but this is like the monitoring component. But I think that gives a good overview of, so HIL is just with controllers. PHIL here is where we get Cinergia in the loop to generate these signals and then feed back in power signals to our simulated model so they can interact with each other.